Okay, so as you've noticed, probably, the unraveled exact couple is a bit unwieldy. Takes a long time to write down, and it's great for chasing specific elements, but somehow it's kind of a big mess. So an exact couple is really a just compact version of all of that data. So let's define it. And really an exact couple is just an exact triangle where two of the things are the same. So this is going to be a pair, D and E. These are going to be some modules. And we're going to have some morphisms. And really I just want to draw a diagram. So I'll say making the triangle below exact. So what does that triangle look like? I've got D, I maps from D back to itself. I've got E, that map I'll call J, and then E maps back to K, and by exact I just mean exact in each spot. So of course that means that the image of I is the kernel of J. It means the, It means the image of J should be the same as the kernel of K, and the image of K should be the kernel of I. So exact in each spot, and I'm just drawing it as a triangle since it wraps around back to itself. From this data, we can define a differential. Okay, well, I want some interesting map, but I don't want to take the composition of two in a row because, of course, I'll get 0 since we have this exactness. So we'll make this differential go from E back to E, which should look like E as in the ER for our spectral sequence. And we'll see why soon. So we'll just do J after K. Notice K after J is 0, but J after K, I'm sort of not following the triangle. I go from E to D by K, and then I jump over and do J. Okay, but of course, this does tell me that D squares to be 0. This is a differential because it's just JK, JK, and KJ is 0, as we just said. Okay, so from an exact couple, we can get a derived couple. So we can form a new exact couple, which we'll call the derived exact couple, or sometimes people just say derived couple. And what does that look like? Well, I want to take D and change it slightly, and take E and change it slightly, and end up with something related but not the same. So I'll have some new maps, I, J, and K prime. And how do we do that? Well, from the old exact couple, what I want to do is let D prime be, let's define this to be the image of I. So that's just I of D, which sits inside D since I maps from D to D. Since I maps from D to D, yes. Okay, and then E prime, we're going to define to be, well, we know we're trying to make a spectral sequence out of this data, so we'll make it be homology of E with respect to the differential, so just kernel mod image. Okay, I've got to tell you about I prime, J prime, and K prime as well. So I prime is just going to be I restricted to D prime, so just I restricted to the image of I. And J prime will make, well, okay, I'm going to put this in quotes, much like the lie I've been telling. I'm going to think of this as J after I inverse. What do I mean by that? Well, J prime is going to map out of D prime, so that's just the image of I. So I take something in the image of I, and what should I do to it? Well, what I want to do is undo the I. So just think of some pre-image X, and then map that over to via J. Well, J lands in E, and I should be getting to E prime, so I'll just take the class, the homology class that I get. So it's the class of J of X. Okay, and then finally, I want K prime. And I'm going to lie about this one as well, so I'll just call it K, but what do I mean by that? It's supposed to take a homology class in E prime, something in the kernel mod image, and it should send it over to, well, I just want to do K to it. That's not quite defined, but I can find some representative Y and do K to that. Okay, well, now there's a lot to check because I didn't even properly define these maps. So I'll leave this as an exercise. I mean, this is really a good thing to run through if you haven't done it before. To check that everything is well defined. So for example, if I had chosen a different representative, that this map still made sense, and so on. And that now we actually still have an exact couple. So this is, again, an exact couple. Okay, so then you just need to check that the image equals the kernel, so on and so forth. Okay, just to give you sort of a quick example so that you believe me now, though of course you could pause the video and do this exercise right now. If I apply K prime to some class that is represented by Y, well, it's supposed to even land in the right place. So I'm claiming I can just take K of Y. And does that make sense? Well, this is going to be something in the kernel of J, because J after K is 0. And so I have something in the kernel, but by exactness, that's the same as the image of I. So this K of Y that I'm looking at is actually I of X for some X. Okay, but that tells me that when I do K of Y, I did land in the image of I, so I did actually get an element of D prime. That's sort of the first thing to check that even makes sense. And now I need to check that it makes sense for different representatives, and so on and so forth. Okay, so we take an exact couple and we kind of play this game of restriction and take homology, and then we get a derived exact couple. But now we have an exact couple, so we can do the same thing. So what we're going to do is just define some differential. We'll make it D prime in this case, and it'll be J prime after K prime. Maybe I should go back up to the picture. So J prime after K prime, that's the same game that we played last time to define our differential. And then repeat. And we could play this game again. Now we have a differential. We could take the homology with respect to that. We take the image of I prime, and so on and so forth. So in this way, we'll build the nth derived exact couple. Let me keep going. Or I guess sometimes it's just called the nth derived couple. I wrote exact last time, so let me be lazy this time. Okay, so this will look like people use upper or lower subscripts depending on which version they're thinking about. I'm trying to think about cohomology, which you'll see in just a moment. So repeat this process and come up with IN, JN, and KN. So these DNs, these are going to be submodules of our original Ds, and these ENs, these are going to be subquotients, right? And we'll do that by defining dr. It'll go from ER to ER. Oh, it's starting to look like a spectral sequence. And it's just going to be JR after KR. And then we'll let ER plus 1 be the homology of ER with respect to this differential. So these are our subquotients. And I said these are submodules. Okay, and so this is starting to look suggestively like a spectral sequence. And we had this question come up in discussion about the grading. Why are these things bi-graded and so on? Well, if the modules that we're looking at here, our D and E, are graded, well, then our ER is graded, right? If we're just working in a category of graded modules, then we're going to inherit some grading. And for us, what is this going to look like? Well, our modules, I mean our, not the ring R, the modules that we've been working with, as we'll see, are bi-graded. Okay, so we're going to be cooking up things like ER, PQ, right? And so our spectral sequence associated to this will also be bi-graded. Or I should say each ARTH page will be bi-graded. But it depends on the context. If you were working in some situation where somehow these naturally were tri-graded or quad-graded modules, then that's what you would end up with in your spectral sequence. Okay, so I keep sort of alluding to this, but let's actually say it for real, which is this theorem that an exact couple is going to give us a spectral sequence. So let's say given an exact couple of bi-graded modules, and of course that means I'm working in the category of bi-graded modules, so my maps should be maps of bi-graded modules. I'll just write D star star. I maps from D back to itself. Then I have some map J to E. That one should also be bi-graded, right? I'm in that category. And then I've got some map K. And let's say here, go ahead and move this up. So I'm going to choose some bi-degrees just to set things up nicely for us. So if this has bi-degree, if our I has bi-degree -1, 1, that means total degree 0. J has bi-degree 0, 0, also total degree 0. And K has bi-degree 1, 0. Remember K, in our old setting, we had named K our connecting homomorphism. So that kind of made sense in our cohomological sense. Well, okay, let me finish this statement before I get to that. So, whoops. Okay, the theorem says, given an exact couple of bi-graded modules, that there is indeed a cohomological spectral sequence. If I change the bi-degrees around, I could say homological spectral sequence, doesn't matter. So ER star star with respect to DR. So that's our differential in the sense that we take ER star star, and this is just the R minus first derived module of E star star. And remember, when we do that, we make DR JR after KR. Okay, so it's exactly the usual setup, and a good exercise in making sure that this makes sense, and just kind of a quick sanity check, is to check the bi-degree of DR, convince you that yes, we are getting that cohomological spectral sequence with the grading that we've been claiming. And maybe another good exercise, this is a different exercise, is to chase through D2 of some element and D3 of some element, what that means. That's probably enough to get the hang of it. Okay, so a good example, as we've seen this situation before, is that we know how to get a cohomological spectral sequence from some filtered kind of object. So we looked at a differential graded module, just a chain complex with some filtration. And notice at this point I'm not saying anything about convergence, so I'm just going to say that there's some filtration. I'm not going to worry that it's bounded. for the moment. Well, in the cohomological setting, we like to set things up so that this was decreasing. But a filtration of A, then we're going to get an exact couple. Well, our unraveled exact couple was just keeping track of all of the data of something we could wrap up all together and say our D's should just be the cohomology of our filtered pieces. Okay, and remember, I did in fact go between those. Actually, let me just copy that rather than write it again, since those should be the same. And then what do I want for E? Well, what shows up on the pages of our spectral sequence is precisely the cohomology of the filtration quotients. And notice I'm thinking about my differential graded module, but the same sort of story holds if I'm thinking about filtering a space. And then these homologies of the filtration quotients are just the relative homologies. Okay, so we get this exact couple, and the claim here is that we get the same spectral sequence that we've been talking about. And notice our differential in that unraveled exact couple was precisely do J after K. Somehow I feel like I wrote that backwards. Nope, do J after K. Because of course K after J is 0, but we saw sort of sewing our long exact sequences together that we could do J after K. Okay, so this is just a short way of containing all of that data. And the derived couple essentially says, go around again, take some submodules in the upper parts and some subquotients in the lower part and define the lift there. But I think of it as, if you do J after K and you get 0, that means that you could lift back through I. Okay, that's less obvious to me in this compact exact couple than it is in the unraveled one. But in fact, because we have this exactness, it's the same argument. Okay, so from an exact couple, we can get a spectral sequence. And we've now seen that from a filtered object, from a filtration on a differential graded module, we can also get an exact couple and the same spectral sequence either way. Okay. In fact, what we'll ultimately see is that from an exact couple, we can also get a filtration. And so really the spectral sequences that arise in these two ways are the same, and it's just a different perspective. All right, let me stop there for now.